The origin and evolution of Earth explains how a hot, barren planet transformed into a life-supporting world over billions of years. Earth formed about 4.6 billion years ago from cosmic material within the solar system. Scientific theories and geological evidence describe its gradual development through stages of planetary formation, atmospheric changes, and biological evolution. Origin and evolution of Earth theories. Various theories explain the origin and evolution of Earth, from early philosophical ideas to modern scientific explanations based on observations, experiments, and astronomical evidence. Nebular hypothesis, proposed by Immanuel Kant and revised by Laplace in 1796, it states that planets formed from a rotating cloud of gas and dust linked with a young sun, gradually condensing into planetary bodies. Revised nebular theory, Otto Schmidt, 1950, and Carl Wieseskar suggested that the Sun was surrounded by hydrogen, helium, and dust. Collisions and friction formed a disk-shaped cloud, leading to planetary formation through accretion. Planetesimal theory, Chamberlain and Moulton, 1905, proposed that a nearby star caused solar material to be pulled out, forming small bodies called planetesimals, which later combined to form planets. Tidal hypothesis, Sir James Jeans, 1919, explained that gravitational interaction between the Sun and a passing star pulled out gaseous material, which later condensed to form planets. Protoplanet hypothesis, H. McCrae suggested that rotating gas clouds formed vortex-like structures that condensed into protoplanets, eventually becoming planets and their satellites. Binary theories. These theories proposed that the Sun had a companion star composed of hydrogen and helium, whose material contributed to the formation of planets through dust accumulation. Big Bang theory, proposed by Georges Lemaitre and supported by Edwin Hubble, 1920, it explains the origin of the universe from a dense, hot singularity about 13.7 billion years ago, followed by continuous expansion and formation of stars, galaxies, and planets. Steady-state theory, proposed by Hoyle, it suggested the universe remains constant over time, but it is now largely rejected due to strong evidence supporting the expanding universe model. Also check, geological time scale. Origin of Earth. The origin and evolution of Earth begins with cosmic events that led to the formation of the universe, solar system, and finally the Earth through gradual accumulation processes. Big Bang event. Around 13.7 billion years ago, the universe began as a tiny, dense, hot point. Rapid expansion created matter and energy, and within 3 minutes, the first atomic particles formed. Formation of atoms. About 300,000 years after the Big Bang, temperature dropped to around 4,500 Kelvin, allowing atoms to form and the universe became transparent, enabling radiation to travel freely. Galaxy formation. Uneven distribution of matter created gravitational differences, leading to clustering of matter and formation of galaxies containing billions of stars spread across thousands of light years. Star formation. Around 5 to 6 billion years ago, dense hydrogen gas clouds collapsed under gravity, forming nebulae. These condensed into protostars where nuclear fusion began at approximately 15 million degrees Celsius. Solar system formation. A rotating nebula formed the Sun at the center, surrounded by a disk of gas and dust. This disk provided the material for planetary formation. Formation of planetesimals. Dust particles collided and stuck together, forming small rounded bodies called planetesimals through cohesion and gravitational attraction. Accretion into planets. Planetesimals combined into larger bodies through continuous collisions, eventually forming planets including Earth through a process known as accretion. Formation of Earth. About 4.6 billion years ago, Earth formed as a hot, molten mass composed mainly of hydrogen, helium, and heavier elements gathered from the solar nebula. Also check, cloud formation. Evolution of Earth. The origin and evolution of Earth continued through cooling, differentiation, atmospheric changes, and biological development that transformed Earth into a habitable planet. Early Earth condition. Initially, Earth was extremely hot, rocky, and barren with a thin atmosphere composed mainly of hydrogen and helium, making it unsuitable for life. Loss of primordial atmosphere. Solar winds stripped away the early hydrogen-helium atmosphere, similar to other terrestrial planets, leading to the need for a secondary atmosphere. Planetary differentiation. As Earth cooled, heavier elements like iron sank to the core, while lighter materials rose to the surface, forming distinct layers through a process called differentiation. Formation of lithosphere. Cooling of the outer surface led to solidification, forming the crust. The Earth developed layered structure including crust, mantle, outer core and inner core with increasing density inward. Giant impact and heating. The formation of the Moon due to a massive collision further heated Earth, accelerating internal differentiation and structural development. Degassing process. Volcanic activity released gases like water vapor, carbon dioxide, nitrogen, methane and ammonia from Earth's interior, contributing to the formation of a secondary atmosphere. Evolution of early atmosphere. The early atmosphere contained very little free oxygen and was dominated by water vapor, carbon dioxide, and nitrogen. Formation of hydrosphere. As Earth cooled, water vapor condensed into rain. Continuous rainfall filled surface depressions, forming oceans within 500 million years of Earth's formation. Age of oceans. Oceans are estimated to be about 4 billion years old, indicating early establishment of water bodies crucial for life development. Carbon dioxide reduction. Carbon dioxide dissolved in rainwater, reducing atmospheric CO2 levels and contributing to further cooling of the planet. Beginning of life. Around 3.8 billion years ago, simple life forms began to evolve in oceans through chemical reactions that produced complex organic molecules. Fossil evidence. Geological records contain fossils of microscopic organisms, including blue-green algae-like structures dating back over 3 billion years, confirming early life existence. Photosynthesis evolution. Between 2.5 to 3 billion years ago, photosynthesis began, allowing organisms to convert sunlight into energy and release oxygen. Oxygenation of oceans. Oxygen produced by photosynthetic organisms first accumulated in oceans, gradually saturating them over time. Oxygen in the atmosphere. Around 2 billion years ago, oxygen began to accumulate in the atmosphere, transforming it into an oxygen-rich environment suitable for complex life. Development of water cycle. Interaction between land and water, including freshwater systems, may have started as early as 4 billion years ago, supporting early life conditions. Formation of land masses. Cooling and solidification led to the emergence of continental crust and dry land, providing diverse environments for life evolution. Biological evolution. Life gradually evolved from simple unicellular organisms to more complex forms, aided by oxygen availability and stable environmental conditions. Atmospheric stabilization. Nitrogen and oxygen became dominant gases, forming the present atmospheric composition essential for sustaining life. Modern Earth system. Continuous geological and biological processes shaped Earth into a dynamic system with lithosphere, hydrosphere, atmosphere, and biosphere interacting in balance.